So this is the end of our first week, 925. We're going to stay in the idea of solving equations. So take a moment, read the do now, and see if you can figure out how much they spent altogether. For time-wise, I'm going to keep going. We'll go ahead and pause if you want to read it and try it yourself. I'm going to read it out loud, and then we'll solve it. It says, Shaumba and Jalen are at lunch. Jalen spent X dollars at lunch. I'm going to write that down. Shaumba spent $750 more than Jalen. It's kind of important. She spent $750 more than Jalen. So Shaumba spent plus $750 to whatever Jalen spent. And well, we know that Jalen spent X, so that must mean Shaumba spent X plus $750. Okay, they spent $50 altogether. How much did each person spend? I would invite a student usually to come up, or two students to come up and explain this. I'll show you what I often see students do. Someone says, well, we need to, the extra $750 is what Shaumba spent more than that. So if we get $7.50 away from $50, we get $42.50. And then we can split the rest between the two people. So take $42.50 and divide it by 2. And you get $21.25. But that's the amount that Jalen spent. Because Jalen spent the X, right? And then Shaumba spent $750 more, so it would be $21.25 plus the more money she spent. So she must have spent $28.75. There we go. And then I would ask, did anyone try to write an equation to do it? And most people don't, but you could have represented this with an equation. You can say that Jalen spent X plus Shaumba spent what Jalen spent plus $750. And we know in total that that was $50. So I do want you to add this to your notes as a way to do it without, well, I have to do the math anyways, but it's a way to do it with thinking algebraically. And then we can add like terms. 2x plus $750 equals $50. And then we can solve it for x. And the cool thing is we do all the same math that the students often do. See how they took $750 away from 50? That was their first step. Yeah, we can do that to both sides of this equation that we wrote. Now to get x by itself, you divide by 2, and this is not what we did. We took the remaining amount and divided it by 2. So x equals $21.25. And again, that's what we said Jalen spent. So it's kind of cool. We're going to start thinking about trying to write equations that represent problems. All right. So in class, we would go over any questions that were for the homework, but I'll post a video separately of me going over the answers to the homework. For now, we are going to talk about, these are same variables on both sides, day 2. So, and we're going to get into some problems in the book. So inside your notebook, you can write 1.5, same variables on both sides, day 2. And after going over the homework, in class, we would then move on to this problem. It says, if all the bag contains the same number of coins, how many coins are in each bag? So, I know we're moving away from it, but I do want to talk about it. because there's some weird things that happen when you have variables on both sides of the equation. Okay, should see it okay. So I would say take a moment with your neighbor, draw the bag and coins in your notebook, and then have a conversation with your neighbor to figure out how many coins are in each bag. For time-wise, I'm going to keep the video rolling, but you can pause it, anytime. Now I'd go each separately. Okay. How many coins in bags is the one we saw from yesterday? How many coins are in each bag here? And I said it was a little confusing. Did anyone figure out how many coins are in each bag? Someone said there are negative coins. I'd be like, yeah, totally. So this might not make sense. Can you have negative coins? And here's what happens. You take 2 bags from this side. You take 2 bags from this side. And you have 2 bags and 6 coins equals no bags or coins? Doesn't make sense. But this doesn't make sense for bags and coins, but we could write an equation and get an answer that would work for math, right? So start back over. Can we write an equation using algebra for this one? Well, yeah. 4 bags, 4x, plus 6 coins, 6, equals 2 bags. Okay. So we have to solve this guy. And if we follow what we were thinking, taking 2 bags away from both sides, totally okay. Bags from bags. Now we have 2x plus 6 equals nothing, but this is where students get confused. We have 0. Okay, now we have 2x plus 6 equals 0. Now how do we solve this? And usually a student has an idea like, well, we got to get x by itself, right? We do have to get x by itself, but here's x. So here's x by itself. What do we do? Well, we were undoing addition first, right? So we'll take away 6 from both sides. Then we get 2x equals negative 6. And then we'll divide both sides by 2. And we get negative 6 divided by 2 equals negative 3. Cool. And so we can't always, bags and coins don't often make sense, but if we write them as an equation, we can still get an answer that makes sense with x. So x in this case, the value that makes it true is negative 3, which does not make sense with coins and bags, but it does make sense with algebra. Awesome. Okay, and we're going to have some more of these ones right here. So you've probably already looked at this one. So the question is, how many coins are in each bag, right? But something kind of weird happens here. If we have 2 bags and 3 coins, that equals 2 bags and 3 coins. Did anyone think about how many bags could be in each coin that would make both sides equal? Well, if you take this away, you take this away, take 2 here and 2 here, well, you have nothing equals nothing. That's kind of weird, right? 0 equals 0. So how many coins in each bag? No coins? Well, here's the tricky part. Let's try to write it as an equation. Or not tricky, but here's the interesting part. If we have 2 bags plus 3 coins, and that equals 2 bags plus 3 coins, look what the equations we have. We have 2 times plus 3 and 2x plus 3. Can anyone think of the number of coins that would work here? Could there be 1 coin in each bag? 1 plus 1, 2, plus 3 is 5. 1 plus 1 plus 3 is 5. Yeah, so we could have 1 coin per bag. Is that it? Is that the answer? 1 coin per bag? Well, could there be 5 coins per bag? Would that work as well? 5 plus 5 is 10. plus 3 is 13. 5 plus 5 is 10, plus 3 is 13. Yeah, it could have been 5 coins per bag. Could it have been 8 coins? Could it have been 15 coins? And the answer is yes, but why? Why is it yes? Well, it's the same on both sides, Mr. Moran. Yes, it is the same on both sides. So, x, because everything works, is actually all real numbers. Every number of any number of coins could work for the bag. 1, 5, 10, 15, 12.5 if it worked. So this is in all real numbers, right? So when we have variables on both sides, we have to watch out that sometimes we get all real numbers. Okay. Did anyone figure out how many coins can go in each of these bags? Would 1 work? Would 2 work? Would 3 work? If you have 2 bags and 2 coins, will that equal 2 bags and 3 coins? And students often say it's not possible. And I would say, I agree, it is not possible. There's no number of coins that can go be the same in each bag that would get us the answer. And I would push you why, and you would say, well, 2 bags and 2 coins will actually never equal 2 bags and 3 coins if the bags contain the same number of coins, right? Because you get rid of these 2 and get rid of these 2, get rid of these 2, get rid of these 2. Now you have 0 equals 1. That doesn't really work. So let's see what it looks like as an equation. 2x plus 2 equals 2x plus 3. And let's do that thinking. 2 times a number plus 2, will that ever equal 2 times a number plus 3? Can anyone think of a number that would work there? Would 1 work here? Would 2 work here? 5? And the answer is no, right? Watch what happens when we solve it, though. This is one way we need to talk about it. And it's just what happens with bags and coins. 2x, take away 2x. And you get 2 equals 3. I don't know, take away 2 from both sides. You get 0 equals 1. And that's not true. And this is not true as well. So we get these not true equations with numbers. And that tells you that x actually has no solution here. Okay, so when we have bags on both sides or variables on both sides, we now open ourselves up to a couple different solution types. We can get one solution, which we've been doing this week. You can get a no solution. Here, no number for x will work. And then you can get all real numbers work. That means the equations are the same, like in B. Oh, I lost B. Where's B? You know, where we have the exact same expression on each side. So every number is going to work. All real numbers. Okay. So, I wanted to take a moment and do these once more, and this is my note for you. So some equations can't be solved by thinking about them as bags and coins, as in the problems above. But thinking is the same. Bags undo bags, so variables undo variables. Coins, integers, undo coin, integers. Oh, should have an S in there. On each side. Okay. So if you can take a moment, add this one to your notes. We're going to solve it. And then I'll give you your classwork, I guess. Yes, that would be good. So write this one down. And we're going to do it one more together, okay, here? So we got to solve this. You can say put all negatives and subtractions. So what do you want to do first? And there's more than one way. Everyone always has a different way. My idea is always to look at the variables and the signs in front of them. And I always try to undo the smaller one. What's smaller, -4 or -2? negative 4 smaller. So what I'm going to do is add 4m to both sides. So that cancels, and we're left with negative 3 equals negative 33. Negative 2, adding 4 to it. So you're at negative 2 on the number line, and you go up 1, 2, 3, 4, right? You get to 2. All right, and then we stop and think, as students get a little stuck here. We're going to try to get m by itself now. Okay, we got times 2 plus negative 33. I'm going to undo that negative 33 by adding 33 to both sides. Okay. Negative 3 plus 33 is the same thing as 33 minus 3, so we get 30 equals 2m. And then divide both sides by 2. And I should see that 2 times what is 30? Well, 15.